Today we're going to talk a little bit about the invertible matrix theorem. So let's say we have a matrix A that's square, n by n, meaning it has n rows and n columns. Then the following conditions are equivalent. So this statement here, these statements being equivalent, that means that either all of the statements are true about a given matrix, or all of them are false. So if you find out that one of these statements is true, then all of them must be true about that matrix. If you find out that one of the statements is false, then they all must be false. Okay, so let's go through the statements really quick. The first one is that A is invertible. The second is that the system AX equals B has a unique solution for every vector B in Rn. Now this notation here just means that B is an n by 1 column vector. That's what this n here is saying. And the elements are real numbers. Okay. This next condition is that Ax equals 0 has only the trivial solution x equals 0. That means if we plug in the 0 vector for x here, of course we satisfy this equation because A times 0 equals 0. But we're also being told here that that's the only solution. You can see that these two statements, B and C, are somewhat related. So if Ax equals B has a unique solution for every B in Rn, well, the 0 vector is a vector in Rn, and we're told that it has only one solution. That solution happens to be x equals 0. Okay, the next statement here is that the rank of A equals n. Then we have that A can be expressed as the product of elementary matrices. We didn't talk too much about this in class, but it's in the list, so I'll list it here. A is row equivalent to the identity. You might be able to think about why A and F here are kind of related. So remember when we computed inverses, so we tried to compute an inverse of a matrix A, we would augment the identity in to the right-hand side here. And then we would do reduced row echelon form. And if A was invertible, we would get the identity on the left and A inverse on the right. Now, getting the identity on the left here came exactly from the matrix A being row equivalent to the identity, meaning that we could do row operations on A and get the identity out of that. If we couldn't do that, if we did not get the identity on the left-hand side here, we would not have an inverse of A. So that's how those are related. And the last one I added here during class is that the determinant of A is not 0. Okay. So we're going to go through some examples using this theorem in specific cases and try to see what we can say about given matrices. All right, so here are the examples we're going to look at today. We're going to determine whether a given matrix is invertible. We're also going to see what we can say about the determinant of each of these matrices. All right, so the first example is we have a 4 by 4 matrix A, and the rank of A is 3. All right, let's scroll up for a second. Now, the statement we have in the invertible matrix theorem that has to do with the rank is that if the rank of A is n, or the dimension equal to the dimension of the matrix, then all of these statements would be true. Okay, let's go figure out what n is in this case. We have a 4 by 4 matrix A. So that means that n in this case is 4. Now we're told that the rank of the matrix is 3, which is not equal to 4. So all of those statements in the invertible matrix theorem have to be false. We can say that A is not invertible. And we can say that the determinant of A has to be 0. Okay? The statement in the invertible matrix theorem said that if, the rank of A being n is equivalent to A being invertible, and it's equivalent to the determinant of A not being 0. So if we're going to go in and negate all of those things, we have to say that A is not invertible, and also the determinant of A is 0. That's the opposite of not being 0. Okay, let's look at this next matrix B here. It's 5 by 5, and we're told that Bx equals 0 has only one solution. Now, I should point out here that the vector x equals 0 is always a solution to a homogeneous systems. Why do I say that? Because if I multiply any matrix, in this case B, if I multiply any matrix times 0, this multiplication here is going to give me the 0 vector. But here I'm told that Bx equals 0 has only one solution. And since I've written down one such solution, there's only one, that means this has to be the only solution. So this is another way of saying that Bx equals 0 has only the trivial solution, x equals 0. So that means that all of our statements in the invertible matrix theorem are true for this matrix B. B is invertible, and determinant of B is not equal to 0. Okay, so now we've got a 6 by 6 matrix C, and we're told that the system Cx equals 0 has infinitely many solutions. Well, we know it has to have at least one solution. When x is 0, that's going to satisfy this equation. But we're told that it has infinitely many solutions. So we don't have a unique solution to this system. In other words, the 0 vector is not the only solution to Cx equals 0. And that violates the invertible matrix theorem, or one of the statements in the theorem. So that means all of the statements, since they're all equivalent to each other, all of the other statements have to be false. So C is not invertible. And we can say that the determinant of C has to be 0. Okay, so next we have a 7 by 7 matrix D, and we're told that there's some non-zero column vector B where the linear system dx equals B has no solutions. Now, in the invertible matrix theorem, if we go back up here, the inhomogeneous linear system, in this case it was dx equals B, needs to have a unique solution for every B in Rn. So if we find just one B, or we're told that just one B makes this equation have no solutions, then this statement is not satisfied. And so all of the rest of the statements are going to be false about our matrix. So scroll back down. So here we're going to say, since dx equals B for some vector B has no solutions, then D is not invertible. We can also say that the determinant of D equals 0. All right, let me just move the screen there a little bit. I hope that kind of helped review the invertible matrix theorem. We'll be adding to this theorem as the semester goes on, but I hope those examples helped clear some things up.